Like, the whole idea is to try and get to an integral that you can do. So that's when you stop. When you're like, oh yeah, I can do that.
Like, you can do the, when you just down from that you do the derivative.
Yeah, I mean, it's hard to.
But I would look at the video, the solution that you had on the video.
Yeah.
And I only did the integrated part like once, and then I did the antiderivative of the next.
Yeah, most of the problems you do, it's just going to be integration by parts once. Most of the problems, like in the homework, is just once. There's a few that you have to do it more than once. Okay, are we ready to get going here? Yeah, that's an enthusiastic yes. All right. Hope you all had a good weekend. I have another handout for you today. These handouts, like I said, are just more problems for you to practice, right? More problems. So why don't you take one, pass them around. Just let them get around there. All right, so today we are starting 6.2. And I'm going to show you here on the screen. Unfortunately, I got to do them separately. 6.2 is called trigonometric integrals. I call them just trig integrals. And trigonometric substitution. All right. Today, we do trig integrals. And then next time, we do trigonometric substitution. They're two separate concepts within the same section. This cannot be done if you can't do this, right? So you have to be able to do this first, and then this will be doable, right? So trig integrals are integrals that involve trig functions, and actually trig functions that are raised to different powers. So we have a lot of preliminary things we have to get in place before we can begin. First thing, can everyone see both these screens? Yes? Okay. Those integrals we should already know, right? The antiderivative of sine x is negative cosine x plus c. The antiderivative of cosine x is sine x plus c, right? Then we talked about how we could generalize this. Actually, I did this a little bit different in class. What I showed you was even more than that. I showed you that if you have the antiderivative of sine and inside of it is a linear expression, right? That the antiderivative would be negative cosine. Oop, I forgot to scale it. Remember I said if the argument was linear inside, you would scale. So negative 1 over a, whatever that number is there. And then the antiderivative would go here. That look familiar, everyone? Yes? Okay, and then the other one is the same thing, with cosine, if you have a linear expression inside. So these things are going to pop up a lot now, and so when we see them, we do not want to invest a bunch of time trying to figure these out. Oops, yeah, sine ax plus b, and then plus some constant. Okay, so all of this we should already know, right? And then there are some others that we'll need to know as well, like the antiderivative of secant squared, tangent, okay, things like that. But this is the main ones I want to talk about. Okay, there's some other formulas we need to know from pre-cal, all right? So I'll just put them up here. So formulas from pre-cal. Okay, we need to know the Pythagorean identities. Sine squared x plus cosine squared x equals 1. We're all familiar with that. And remember that this identity can be written many different ways. You could write it this way. Sine squared x equals 1 minus cosine squared x, right? All you do there, that's just solving for sine squared. Move the cosine squared over, right? You could have solved it for cosine squared. and then it would have been 1 minus sine squared x, right? So all of these are the same equation, just written 3 different ways, right? Okay, there's another Pythagorean identity from pre-cal. Tangent squared x plus 1 equals secant squared x. This one we don't use as much in pre-cal, and in calculus we didn't use that much in Cal 1. But here we're going to use this a lot. Does that look familiar to you all? Yes? Okay, this formula right here, again, we can move things around. We could say tangent squared x is secant squared x minus 1, right? We could move the 1 over to the other side. So in this one, it's solved for secant squared, right? And in this one, it's solved for tangent squared. But they're the same thing, right? Okay, what else are we going to need? More pre-cal formulas. We're going to need this really important formula, sine, let's see. By the way, I have these on here. These are on the notes. Let's see, I don't want to talk about any of that yet. They're right here towards the end of, before we get to this to the examples. Let me move it over here. Where is it? There we go. These are called the half angle or power reducing formulas. I would like to write these on the board, and it'll be off camera, but it'll be at least on the board so I can access them if I need them. So in pre-cal, we learned that sine squared x equals 1 minus cosine of 2x over 2. This is, in some books it's called the half angle formula. Other books it's called the power reducing formula. I like to call it the power reducing formula because what happens is you have sine squared x, and in your new expression you don't have it squared anymore, right? But what happens? You have to double the angle in here. So there's a kind of a give and a take for it. And then for this, we can rewrite this as 1/2. In other words, pull the 2 out front as a 1/2, and then just write 1 minus cosine 2x. I'm just going to put it like that. That's the formula. Yeah, that's the first one there. And then you could of course distribute that 1/2 through, right? In which case you get the second one on top there. Far right top. So that one we'll need. And then similarly for cosine squared x, it can simplify to be this. So the only difference between these two formulas is this has a minus and this has a plus. Okay, those are the only differences. So I know it's been a while, but we need to remember those, all right? All right, here we go. So I'm not going to go through the notes and go through all the strategy and all that. I'm just going to give you a problem to start, all right? So what if I put this up? What if I put sine to the 4th power x cosine x dx? All right, this is an example of a trig integral. It's an integral. It contains nothing but trigonometric functions, right? We have sine to the 4th power x cosine x dx. We look at it for a second. We're like, okay, how about basic u sub? Right, that's one of our first techniques. Is there a basic u substitution I can use here? Do you see something and its derivative? No? Yes? What's the derivative of cosine x? Negative sine. Do you see negative sine? You're off by a constant, but isn't it to the 4th power? So it's kind of trapped, isn't it? That sine is kind of trapped. So that won't work. How about the other way? Can you look at this as sine x? And then what's the derivative of sine? Cosine. In other words, I can look at this more like this is sine x to the 4th power times cosine x dx, right? And now do you see it? If u is sine x, the derivative is cosine. It's not trapped, right? I mean, it's actually perfect. It's not off by a constant. So I could just use a basic u sub here. U is sine x, right? Derivative of that is just cosine x dx. Remember, I'm using u sub here. I'm not using, what did we learn last time? Integration by parts. I'm just using basic u sub. And if I do this, this integral just becomes u to the 4th du, right? There's nothing, I don't have to scale anything. I replace the sine with u, replace cosine x dx with du, and I'm there, right? The antiderivative of u to the fourth is 1/5 u to the fifth plus c. And then that's just 1/5. And how do we write this? This is sine x to the fifth plus c. You all follow it? And I don't like that notation. I'm going to use a notation that everyone uses when you raise a trig function to a power. Oops. I'm going to move the 5 like that. There we go. Okay, is that pretty straightforward? Basic u sub? Yes? Okay, let's do another one. How about this? Oh, shit, I don't know what. I need to wake up. Okay. How about tangent to the third? How about tangent to the third x secant squared x dx? Very similar problem. Do y'all see the basic u sub? Tangent. U is tangent, because if u is tangent x, the derivative of tangent x is secant squared x, right? And so it's right there, right? So u is tangent x, du is secant squared x, dx. And so I'm going to go a little faster here. How could I rewrite this integral in terms of u? U cubed du. And the antiderivative of that is 1/4 u to the fourth plus c, which is 1/4. Now u for us was tangent, so this should be tangent to the fourth x plus c. I'm going fast because I normally don't show these when I teach this section. I just want to make sure we can do the basic ones first. Basic u sub, yeah? Let's do one more. So this one was to show you that you could do a basic u sub with sine. If you have sine and cosine together, you should be able to do some sort of substitution with either sine or cosine, right? Like if I switch this and I put the 4 on the cosine, then we would do cosine as our u. And du would be the sine, and we'd be off by a constant, but we could still do the same sort of u sub. How about this one? How about, this one's going to be a little harder. How about tangent cubed x secant x dx? This one's a little harder. Hold on. I messed this up. Sorry. I want these reversed. Secant x tangent x, sorry. Yeah, so if you try right now what we did here, right, with u being tangent, that does not work, right? Why does that not work? Derivative of tangent is secant squared, I have secant cubed. You were saying, can we pull the secant apart, right?
Yeah. Well,
We can pull it apart.
What I was thinking, but that'll work too.
All right, so can we pull it apart?
Yeah.
Okay, let's try that. If we pull it apart, how do you want me to write it? Secant
Secant x and then secant x.
secant x, and then you want me to write secant squared x, and then tangent x dx, like that. We could do that, right? Now, if we let u be tangent, right, the derivative is what? Secant squared here, right? So we should be able to rewrite this as u. This and this will be du, but we have a problem. What's this? Yeah. Yeah, it would be a different variable, which is not good, because we'd have u's and x's mixed together. Y'all see that? So y'all see that this won't work if I let u be tangent? So what else could we do? Could we let u be secant? Let's try that. Let's just see. If u is secant x, you need to know what the derivative of this is. What's the derivative of secant x? Secant x tangent x dx. Do you see that somewhere? Yes, look, check this out. This is u, right? That's our u. That's this right here, right? Now it still needs to be squared, yes? But do you see that what's in green? Secant x tangent x dx, that's du. This is our secant x tangent x dx, right? All of that together is du, isn't it? In other words, if I wrote this way, secant x squared times secant x tangent x dx, then hopefully it's a little more clear. You have your u here that's going to be squared, and then you have your du right there. Do you see it? U squared du. So this will become integral u squared du, which is 1/3 u cubed plus c, and then replace u with secant x. So 1/3 secant cubed x plus a constant. Okay, so what's the moral of the story so far? The moral of the story is that if we've got sines and cosines together, when we're probably going to make a u substitution of u is equal to sine or u is equal to cosine, right? If we've got tangents and secants together, we're either going to make a substitution of u is tangent or u is secant. It just depends on how the powers work out. And that'll help us determine which of these we're going to do, all right? Now let's get into the section, all right? So what this section does is they give you a set of steps. They give you not steps, but like if you see this, try this. If you see that, try this. And I like that, but I'm gonna start with just an example, all right? And then as I go through the example, I will refer back to the steps, all right? So let's do part A there. So what we see here is the integral sine cubed 4t dt. And right away, you should recognize that we don't have sines and cosines, right? We've got just sines. And so we can't really use what we did before, right, with sine and cosine, because we don't have the cosine. And is there anything else I could try? Like this isn't just like a basic formula, right? I don't know this from Cal 1. Like what's the anti? Yeah, this is an ax plus b. This is a linear expression. So we do know that if we ever do have a substitution of sine or something, that we will have to scale by the 4. We'll have to do a 1/4.
But would it not just be like the formula plus the cube?
No, because of the cubed. The cubed is what causes the problem, right? So let's just say we tried something. Let's say we said, okay, I know the antiderivative of sine is negative cosine. So negative 1/4 cosine, then what do I do with the power? What are you thinking,
Would you not just,
fourth power?
yeah.
Fourth power, but wouldn't you need another 1/4 out front or something? Because isn't the antiderivative of something to the third 1/4 that to the fourth? So you need another 1/4 out here? I'm just trying to say if you're following that logic, right? But do you see that if you take derivative of this, you're not going to get this?
Yeah.
Because of chain rule, right? The 4 will come down. You'll have this thing cubed, right? You'll have this thing cubed. That's not this. And then you'll have the derivative of this, which is sine. Oh, I'm missing my 4x in here. But it doesn't work. It doesn't work. If it was just sine, yes, right? If it was just sine, we just use the formula from the beginning of class today. Okay, so what do we do, right? What do we do? Well, we can use these if we see squareds, right? We have cubes right now. We could split up the sine. We could do this, right? So look, we're going to do, let's try it. Let me write it this way. Sine squared 4t times sine 4t dt. Y'all agree I can do that? There's nothing wrong with that algebraically? Now, if we were to use this formula here, if we were to do it, right? I'm going to write it down, but don't write it down. Let me show you what it would become. What would this become if I use that formula there? And I want to use this one right here. I would have 1/2 parentheses 1 minus cosine of what? 8t. Because whatever this formula says, whatever your argument is here, it's double that argument. So if we had 4t in here, 4t here, this would become 8t. Right? We could do that. There's nothing wrong with that in terms of algebraically that is true. The problem is that we still have this here. And now our arguments are different. Do you see that? We have a cosine 8t and a sine of 4t. And so those are different now. It's going to create a problem for us. Could you do u sub? Well, if you did u sub, like, what would you want to use for u? Oh, above here? Okay, let me erase this. If we did u sub here, what would be your u?
Sine of 4t.
Sine of 4t? And so this would be u squared. But the derivative of sine of 4t would be cosine of 4t times 4. And we don't have a cosine of 4t, do we? No. Right? So does everyone appreciate the problem we have here? Like, do y'all see that we're kind of a little stuck? Yeah? Sure? Okay. So what I'm going to do is, well, I took it off the board. I'm going to use this over here. The Pythagorean identities. Remember, we said we could take that, we could solve for either sine squared or cosine squared. If I solve for sine squared, what is it? 1 minus cosine squared, right? So this sine squared right here, I'm going to rewrite it as 1 minus cosine squared of 4t, right? And then leave the sine 4t alone. Now do you see the u substitution? You can let u be the cosine 4t, not the squared, just the cosine 4t. The derivative of cosine 4t is what? What's the derivative of cosine 4t? Not antiderivative, derivative, because we're going to do basic u sub, right? Derivative of that should be negative 4 sine of 4t, right? That's the derivative of that. And I have that out here, don't I? I'm off by a constant. So let me try it. So I'm going to let u be the cosine squared. No, not the squared, right? I don't want the squared because that'll get me chain rule going on. I don't want chain rule. I just want this piece right here. That right there is my u. The derivative of that is negative 4 sine 4t dt. I'm taking the derivative, not the antiderivative, right? Because it's a basic u sub. Now I try and match things up. This right here is u, right? And that's this thing. So what is this expression in the parentheses going to turn out to be when I make my substitution? 1 minus u squared, right? That's going to be 1 minus u squared. Okay, great. Now we need to figure out what this becomes. And I see that I have sine 4t dt here, right? That's this. But this negative 4, I'm off by a constant. I can take care of that, right? I can divide both sides by negative 4. Or multiply by negative 1/4, however you want to look at it. I like to look at it like this. And now it matches exactly, doesn't it? That is going to be replaced with that. Yes? So now this becomes integral. Okay, 1 minus, we said that was going to be u squared. And then this green part becomes negative 1/4 du, right? That's it? Negative 1/4 du. You have choices here. You can pull the negative 1/4 completely out of the integral, if you'd like. Or you can distribute it through here to here. What do y'all want to do? I don't care. Both ways are fine. You want to pull it completely out? Okay. Let's pull it completely out. We have equals negative 1/4. I still have the integral 1 minus u squared du. And how do you do this antiderivative? Well, there's subtraction, right? Just one at a time. What's the antiderivative of 1? Antiderivative. Careful. It's u because what's our variable? It's u, right? So the antiderivative of 1 would be u, not x, right? And the antiderivative of u squared would be 1/3 u cubed. And then we still have the negative 1/4 in front of everything. So negative 1/4, parenthesis, u minus 1/3 u cubed, right? All that plus c. And now replace u with cosine of 4t. And we're done. So this becomes negative 1/4 cosine 4t minus 1/3 cosine of 4t to what power? Third power, so I'm going to write it like that, plus c. I can't see myself over there. I think. Okay, yeah, that does come on camera. All right.
What would have happened if you had distributed that -1/4? It would just.
You just have to keep track of it while you're doing the antiderivative, right? It would have been negative 1/4 plus 1/4 u squared. That would have been your integral, right? So antiderivative of this would have been negative 1/4 u. The antiderivative of this would have been 1/12 u cubed, right? Because the 1/3 hits the. That's it. I mean, and we would get that if we distribute if we distribute this through. That's exactly what we would get, right? All right. Yes? Okay, so let's now go and scroll up and look at the steps. Look at that one there, and then over here. Okay, so it says part 2. I'll do a part 1 in a second. See part 2 there? It says if you look at an integral and you have sine to a power, and that power is odd, what are we going to do? Use the Pythagorean identity. Why? Why? Why is that always going to work with an odd power? Like let's say it's sine to the 5th, right? If this was sine to the 5th, how would our problem change? Yeah, if this was to the 5th, right, how would that change this step? What would that be? That'd be sine to the 4th, wouldn't it? Okay, and then here, here to here, does the Pythagorean take you from here to here? No, it doesn't. Shit, so it's a little different. Maybe we should work through this one. What?
The 1 minus cosine squared, would that whole parenthesis be like this squared?
Yes, it would be this whole thing squared, exactly. What we would do is we would say, okay, this is like having sine squared 4t, but then squared, right? So that's what sine to the 4th 4t is. It's sine squared 4t squared. So it would be this squared. Okay. Is that all right, everyone? By the way, on the Pythagorean identity, if this is a 4 and this is a 4, is this still 1? No, not with the Pythagorean. Pythagorean, it must be squared, squared. It can't be anything else. Okay? So you can't just say, oh, this is a 2, this is a 2, I'll make that a 3 and make that a 3, or make that a 4 and make that a 4. It only works with 2. All right? And it comes from the fact that it comes from the right triangle, right? That a squared plus b squared equals c squared. This is your a squared plus b squared equals c squared. It's not a to the 4th plus b to the 4th equals c to the 4th. So, okay, so that would change that. How would it change this line? Squared, okay. Now things would be different, right? Because you would have to handle this. How would you handle this? How do you take care of 1 minus u squared squared? Just expand it out, right? Just multiply it out. 1 minus u squared times 1 minus u squared, FOIL it out. And then you would have just a bunch of additions and subtractions, and you just do them term by term. So it would still work, all right? All right, we'll have an opportunity to practice, but I'm just trying to get you to see why when you have an odd here, this will always work. Because if you have an odd, you'll always be able to pull one factor out, which means this power will be even, right? And then you can somehow use like squared squared or squared to the maybe 3rd, which would be to the 6th or something like that. This will be able to be handled somehow. And you'll have this right here will be your little du sitting on the outside. Okay, so I hope that note makes sense. If you scroll down on that note more, it goes through more of the detail. I'm only going to be able to scroll one of these at a time, but it says here, if you do that, factor out a sign, right? Factor out a sign, and then use that Pythagorean identity, right? And then make your substitution, let u be the cosine, which was what we did, right? U was cosine? Okay. You are allowed to have formula sheets, right, on your test? One of the formula sheets has all these steps on it. It's one that you have to print out. It's not on that. It's not on the packet of sheets. It's a separate sheet that says, does anyone have it printed by chance? No? Okay. So it's online in our Canvas shell under Files. There's a sheet that says trig integrals or trig summary or something like that. Print that out. You can have it on test. It has all these steps. Okay. Well, what if you have cosine as odd? What do you think? What if you have cosine to an odd power? Let's do one with cosine to the odd. I will make one up. Let's make it ugly, yeah? Y'all ready? Jump right into the frying pan here? Let's do it. I'll make it easy in some respect, but hard in other. How about the antiderivative of cosine to the 7th x dx? So it's hard in the sense that it's 7th power, but I'm keeping it easy because the argument inside is just x. It's not like 5x or beta x or something like that. All right, so I look at it and say, hey, look, okay, I don't know what this is just off the top of my head. I don't know what it is. So since I see odd, if I were to peel one cosine off, then the other cosine would be an even, right, to the 6th power. And the Pythagorean identity allows me to deal with even powers somehow. So I'm going to somehow use a Pythagorean identity here. So it'll be cosine to the 6th x cosine x dx. All right. This cosine x dx, that cosine you peel out, that's the derivative of your u. So what should u be for us? This will be the derivative of it, right? This is the derivative. This part on the outside is the derivative of whatever I'm going to let u be. So u would need to be sine, right? So I need to somehow get that rewritten in terms of sine. So I'm going to rewrite this like this. Cosine squared x to what power? Cubed. And then cosine x dx. How can I rewrite cosine squared x using the Pythagorean identity? Cosine squared x is 1 minus sine squared x, but that's all cubed. And then cosine x dx, right? And do you see right now you can make your u sub? Right now. Because I finally have something and its derivative. Something and its derivative. Here comes the u sub. U is sine x. Du is cosine x dx. So what does this new integral become? Integral, say it again?